Hi, an important expression regarding single tune amplifier, single tune amplifiers and expression for the voltage gain. So in order to search for that expression, a beginner need to have an idea on some basics, some sort of basics, okay? If what is a resonance frequency, the tune amplifiers works on that principle of resonance. And what is resonance, guys? If you have an inductor, the impedance offered by the inductor XL will be omega L, isn't it? And on the other hand, XC, what is XC? 1 by omega C. So here, watch carefully, the frequency component is over here, 2 pi f is over here, omega equal to 2 pi f, isn't it? And here we have that 2 pi f. So as we go on, increase the frequency of the circuit, like the tune circuit. As we go on, increase the frequency, XL here, the frequency, as we go on increase the frequency, even the reactance offered by the inductor will be increasing, whereas with the increase in frequency over here, the XC provided by the capacitor is decreasing, in the sense with one function being increasing, XL is increasing and XC is decreasing. So at a particular frequency, these two magnitudes will be equal. So sorry, though both the reactances will be equal, that is XL will be equal to XC at a particular frequency. One factor is increasing and another factor is decreasing. So at a particular frequency, these two will be equal, and that particular frequency, the frequency at which the reactance offered by the inductor and capacitor are equal, is known as a resonance frequency. Right? So f will be some specific to say that it is happening, it's the resonance frequency f naught, right? And it will be omega, the corresponding omega, it will be omega naught. At resonance, f will be f naught, omega will be omega naught at resonance. Remember this point very much. This word, what specific, some sort of notation, like okay, frequency, working frequency, at a particular frequency this phenomena happens, and that particular frequency is known as resonance frequency, and it's a f naught or omega naught in 2 pi f, right? So this is what happens with the resonance. Resonance is the condition at which XL will be equal to XC and omega L will be equal to, sorry, not the suffix, I'm very sorry, omega L will be equal to 1 by omega C. We need to make use of this condition, okay? At resonance, this comes into the picture at resonance. And on the other hand, that single tune amplifier, how the circuit looks like. So guys, R1, this is for simply to provide the bias, proper biasing condition, R1, and we have RE also, and we have that capacitance bypass capacitor CU also, right? So in the place of this one, here at the capacitor point, we have a tank circuit. This is known as a tank circuit, this combination is known as a tank circuit, and we have this one, okay? We have a ground over here, and this is for plus VCC, okay? So that's what the circuit. Now for AC analysis, as far as AC analysis is concerned, DC is made 0, DC is 0, grounded, DC is made 0, okay? So remember that one. For AC analysis, we don't have DC, in the sense, guys, this is DC, VCC is the DC in the circuit which we are working on for the time being, and this is grounded, that's removed and grounded, and even this side we have a ground, right? So a capacitor C and inductor L. Okay, so with this arrangement, what happens is, so guys, this flips down, see, ground, here is the ground, it comes down, R1 is like here, so that will come like here, that comes down, this R1 is grounded, like that will come in shunt with R2, R1, it was grounded the other side, isn't it? So here ground, it comes down. This is the modification in the circuit which we see when it comes to that of AC analysis. It's all about AC analysis, okay, not the DC. We are working on frequency components, and so it's a frequency analysis, okay? And guys, if this is the condition, like we have Rin of the transistor, right, between base and emitter, Rin, we have that Rin over here, input resistance of the input impedance offered by the transistor terminal between base and emitter, Rin, input resistance. So the parallel combination of this one, we select the values of R1 and R2. These are external resistors, and we can select the values of R1 and R2 in such a way that the parallel combination of R1 and R2 is very much greater than Rin. So with this condition, this becomes this value of resistance becomes insignificant when in shunt with Rin, right? Two resistances like this one, two resistances in shunt with each other, very high value, 10k and 1k. The parallel combination, the approximate value will be approximately equal to the lower value 1k, isn't it? So in the same way, we select the values of R1 and R2 in such a way that has no significance when compared with Rin. So we don't need this one also for the analysis part, okay? And on the other hand, it's a AC analysis, and the capacitor will be a short circuit. Here the capacitor will be a short circuit from, if this is the point from, and ground potential appears over here. So we don't have this one because ground potential appears over here. It's so grounded on either side with the capacitive capacitor property for AC. So we don't have this one also. This gets short circuited. Ra doesn't exist, so only we consider this transistor and the tank circuit for the analysis. Okay, so the transistor is replaced with the hybrid pi model, not the H parameter model. H parameter model is for the lower frequency analysis. So here it's all about high frequency analysis. So we make use of the hybrid pi model of a transistor. The beginner is suggested to have an idea to refer that hybrid pi model before going to start with this transistor. Okay, now this is grounded, so we'll have to make use of hybrid pi model over here. And before going to the analysis, actual analysis which we are in search of, some fundamental to be known about an inductor. A pure inductor, that's simply R. Having a pure inductor practically isn't possible. It's really impossible to have a lossless inductor. That loss has to be represented, okay? And how to represent that one? We have an inductor and the loss in series, Rs. Right, we have an inductor L, and we can we need to bother about resonance. When it comes to that of resonance, two types of resonance, isn't it? Series resonance and parallel resonance. We have to evaluate the relationship between these two, then we have to plug in, making use of that one. Something else comes into the picture. So going for the parallel resonance also. R is simply the loss represented by the inductor. Okay, so we have a inductor and Rp. So obtaining some relationship. This will exist at resonance. The series combination will be equivalent to the parallel combination at resonance. Yeah, we'll have to evaluate the relationship between the series representation and parallel representation. Then we'll have another important equation that has to be plugged in over here. All right, so guys, okay, let's do this one, but an important equation to be noted down during this process itself. We have to note it down and then plug in that conditions somewhere else in the ongoing discussion. Okay, so what is the expression for quality factor? Yeah, we need, when it comes to that of inductors, if you are dealing with inductors and capacitors and all, there is a need of considering what is a Q value, quality factor, which is the index for the performance of the capacitors and inductors, right? So its general expression for Q is, what is that? Reactance offered by the inductor XL by the resistance, XL by R. Right, so what do we have? And XL is omega L by R. So at resonance, what happens? This comes into the picture at resonance. So we have another form for R, like XL will be equal to this R as it is, but omega L at resonance, what happens? This condition for resonance, omega L is equal to 1 upon omega C, 1 upon omega C, right? So guys, remember, this omega L by R is a Q value according to the definition. Omega L, wherever we have omega L by R, the ratio omega into L upon R, that can be written with the one letter q, right? Even reciprocal of omega into c into r, even this, if we find this product, we can, like, this ratio can be plugged in with q. Not only that one, something else comes into the picture. We'll have to make use of the equation for q, right? So here to go ahead with that one, we'll have to consider the impedance z. It would be better, rather than evaluating y, the admittance, rather than this one, there is some simplicity, okay, which is equal to 1 by z, which is equal to what? What is z actually? Z is the impedance, the series, isn't it? So rs plus, what is that, j omega l z. So y, which is equal to the reciprocal of this one. So what is that? How to write down that? So y, which is equal to 1 by z, will be equal to 1 upon rs plus j omega l. All right. So guys, taking out this factor, this as common from this term and this term, what do we have? Y, which is equal to 1 upon z, which is equal to taking out j omega l as common from this and this. So from here it's a 1 plus rs as it is, okay, j omega l is taken out as common from both the terms, isn't it? So 1 from here, so it's 1 plus rs as it is, so j by j omega l came out, right? Is that clear? Now guys, this can be, what is this? So j can be written as negative j, right? 1 by j, negative j. If you have a question, what we have, 1 by j into j into j, will that be a problem? No, isn't it? So j into j, that's a negative 1 j, and this one negative j. So that's what we write it. And guys, can you see this? Can you see something? What is this ratio? What is this ratio? There, omega l upon r, and this is the reciprocal. So this can be y, which is equal to 1 upon z, which can be written as 1 upon j omega l as it is, 1 minus j, and it's a reciprocal of q here. Omega l by r equal to q, r by omega l, that's 1 upon q. All right. Right, there is a need of rationalizing this one, the complex term, into 1 plus j 1 upon q, even the denominator 1 plus j 1 upon q. So will that be okay? So do we have, yeah, as we go ahead, this y, which is equal to 1 upon z, will be equal to, guys, this one, what, this is as it is, okay, j omega l, and this is a minus b into a plus b, and this is as usual, okay, no change in this one, 1 plus j 1 upon q, no change in that one. This is a minus b into a plus b, so a square minus b square, in the sense, open the bracket for this one, this is okay, a minus b into a plus b. So writing this for these two products, okay, it's like open the bracket, it's 1 a minus b into a plus b, a square minus b square, so 1 square 1 minus this into this, j into j, that's 1 negative 1, so that negative and this negative becomes positive, and it's a 1 upon q square, okay, q 1 upon q into 1 upon q square. So this is the one, this is a reduction over here. So guys, for q value, we have this q value, okay, it will be some 10, 15 like that, q values. If we select an inductor for any purpose, it has some q value specified by the manufacturer. If q value is greater than 1, if you select the inductor and capacitor's value in such a way that its q value is greater than 1, let it be 9, 10 like that. So this ratio, q greater than 1 in the denominator, and this becomes insignificant, right? This will be very low, and so this will be very low value, and yeah, this can be neglected. and this can be neglected. So what do we have? Y, which is equal to 1 upon z, which is equal to, so guys, we don't have this anymore, and it's like it's getting multiplied, isn't it? It's getting multiplied in the sense 1 upon j omega L plus j, this one j 1 by q from here is multiplied with this one 1 by j omega L, right? So we don't have this anymore, so finally y, which is equal to 1 upon z, is equal to 1 by j omega L plus what that, this got cancelled, so 1 upon q into omega into L, right? So guys, this is from the series combination. And on the other hand, how to write down this one? So we don't need this anymore, okay, because we have that expression, and now the focus is on the parallel combination, right? So what is the admittance of the parallel combination? Y, which is equal to parallel, so this can be written as 1 by Rp plus 1 by XL j omega L. So I said this is equivalent, these two are equivalent. So see, can you see this? Y equal to this, y equal to this. We have 1 upon j omega L, 1 upon j omega L. So this one, it's a y, and this equation, it's this equation. So definitely this has to be equal to that, isn't it? So equation 1, from equation 1 and 2, like that. So this is y, and 1 upon j omega L, 1 upon j omega L. So what is left over? This is left over, that should be equal to that. So here I am erasing here itself, okay. See, this isn't, yeah, that is equal to, which is equal to 1 upon q into omega into L, right? So from here we have another form of q from this equations and all. What is now that Rp will be equal to q into omega into L, right? And so q will be equal to, here from this expression, q will be in parallel, and we have another form of q, Rp by omega L. So guys, even this is, I didn't manipulate, okay, I'm not saying that this is this, no, we got the expression, and even this ratio will be q, right? We have those ratios and even this ratio, and yet there is another important ratio also. At resonance, what is this? At resonance, what is this? Omega L will be equal to 1 upon omega c, isn't it? At resonance, here omega L will be 1 upon omega c, and q has another form, Rp as it is, this omega L will be equal to 1 upon omega c, that flips up, so omega into c, something like that. So finally what I want to say is that even this product, if you have a omega multiplied with R multiplied with c, even if we find a cross in the due course, in the ongoing discussion, if you find this product, even that can be plugged in with a q, right? So make a note of this one, omega Rp, R into c, it may be, it's Rp, but finally what I want to say is that omega multiplied with resistance multiplied with capacitance, it may be equivalent or something like that, capacitor, right? Omega into R into c, even that is a q, R upon omega L, even that is a q, and omega L, like that, okay. We'll have to make use of all these, right? So yeah, finally this one, this is very helpful in simplifying the expression which we are in search of here in this context, okay. So here, this one, we need to have y, because I'll have to show you later on, yeah, this is the reason I have changed the equation according to all these equations, okay. Now the transistor, so guys, now the transistor, focus on this one, okay. There is a small modification over here. Now the transistor is replaced with the hybrid pi model. The transistor should be replaced with the hybrid pi model. How the hybrid pi model looks like? It's a common emitter configuration, and we have the base over here, we have the base and the virtual base B dash, What exists between B and a B dash? Here we have a, what is that? R B B dash, and emitter is common to both input and output. We have the emitter part over here. We have the emitter over here. Okay, so let me make it a short. We have that virtual base B dash, B dash. Okay, and here emitter is common to both input and output, and we have the capacitor C. Very sorry, the collector terminal C, and IC will be flowing with the, what is that, the current generator. You need to have a idea on hybrid pi model. Okay, I cannot explain all these, it's already done. Find it. GM V B dash E, according to the construction, and we get this one. And what exists between B dash and C? We have a resistor. R B dash C, right? And also a capacitor, C B dash C, between those two terminals, B dash and C. And even here B dash, we have R B dash E, isn't it, between virtual base and emitter R B dash E. That's right, right? And here guys, this is the V in to the transistor. Here we have that V in to the transistor between base and emitter. This is not the external voltage, that voltage which reaches the base and emitter, the input voltage to the transistor, not the source. Okay, not the source, not this one. This is V in, is the voltage which appears across base and emitter, which is the input voltage to the transistor. That V in I'm talking about. Okay, so V in appears over here, and there is some another voltage to be considered over here. Between virtual base and emitter, we have V B dash E, okay, across here. And from here itself we'll have a very important equation. What is that? According to potential divider rule. See, according to potential divider rule, what we have is V B dash E will be equal to the supply voltage, as far as this arrangement is concerned, V in into the resistance R B dash E by the total resistance. What is that? R B dash plus R B dash E. A very important one. Okay, we'll have to make use of this one, right? So this is what happens with the input. We'll have to make use of this expression in the ongoing discussion. And on the other hand, what resistance over here? We have a resistance, guys. Here, see, time to have a much focus on this one. We have a resistance between collector and emitter, R C E, from the beginning. Okay, not yet reduced. And also we have other than this one, this is okay, but we need to consider this one also, from the collector to the ground. See, here we had a collector terminal to the ground, collector to the ground. Now this will be grounded. Okay, so we have a inductor L and capacitor C from the tank circuit. I need this place. So Q will have, what are the forms Q has? From Rp by omega L, even that is Q, Rp. It's a resistance, Rp by omega L, which is equal to omega Rp into C. Even this is Q. Okay, Q has these many forms, these many stupid forms the Q has, right? So here guys, even this is Q. Okay, even this is Q. Yeah, even this is Q, right? So this RB dash C, which is common to the output and input, can be replaced with some other resistors in the input and output according to the Miller's theorem. No much focus on that one other than this statement. No proof for that one. I have already proved it. Miller's, making use of Miller's theorem and all. Okay, so what I want to say is that take it away, plug it out, make two pieces. Some part of this can be placed in the output, and some part can be placed in the input, right? So that resistance appear because of this one, that resistance which appears across the output, because of this one, okay, let that be R mu something Rm, Miller's resistance. Not only this resistance, some other resistances also comes in between. Please check it. And even the capacitor we have, even that capacitor can be split, okay, even the capacitor can be split, and that is Cm, saying that that capacitance came into the picture with Miller's reduction, right? So guys, so this is also done. We don't need this anymore, right? Even in the input, but for the analysis part we need only the output. We are in search of, now that V naught appears over here, that V naught which we are in, like V naught will be appearing over here, okay. So this is the resistance from the beginning we have from the hybrid pi model which is existing in the circuit for the hybrid pi model, and this is the resistance which came into existence with the Miller's reduction, making use of Miller's theorem, okay. So a small reduction over here, a small change, we don't need this anymore, okay, we don't need this because this was the equation which we are in need of in this analysis. Now here way to draw that. So guys, no change in that one, no change in that what, no change in that Gm V P dash E, no change in this one. So we are done with this one, okay. So guys, can you see these two resistances Rm, this one, even this is resistance and this is resistance in the parallel combination, and it may be some other resistances in the discussion, right? It may be some other resistances. We have a resistance from the beginning in the hybrid pi model, and this came into existence making use of the Miller's theorem, Miller's reduction. So that one is represented, that these two resistances represented like saying that it's a R total. We have R total, the parallel combination of whatever resistances we have, right? That will be going in detail, will be in need in solving problem only. We are doing some derivation. So here we are done with these two, okay, we are done with these two, and we have a inductor there, only one inductor, no parallel combination of series combination like that. We have an inductor L here, it's placed over here, L, inductor L, right? And we are done with this one also, we are done with this one also. So two capacitances, the resultant, the parallel combination of whatever can be replaced with one capacitor, can be replaced with one capacitor, giving the name C equivalent, and this is the place where we evaluate, obtain the V naught, the reduction for that one. From here we can make use of we can derive that expression which we are in search of, right? So guys, we need this one. What is that? We have that expression B dash E is equal to V in into R B dash E by R B dash E plus R B B dash, okay. So here what is that expression for V naught? V naught can be written as here, V naught can be written as this is a current multiplied with Z. It's a current multiplied with Z. What is that current? Gm V B dash E, okay. This is a current multiplied with Z, multiplied with Z. We will have to evaluate this Z, then plugging in, and in that Z we have that V in, and the ratio V naught by V in gives us the voltage gain, something which we are in search of, right guys? So if these if this is the arrangement, it would be better to evaluate admittance rather than impedance. So y which is equal to 1 upon Z, and at a point we can take the reciprocal and that will give us Z, that Z can be plugged over here, okay. So y which is equal to 1 by Z, which is equal to 1 upon RT plus 1 upon XL for this one, plus 1 upon XC for this one, okay. we notice that. So yeah guys, I need this place. All right guys, so this is the one. And so y will be equal to what is that, 1 upon rt plus 1 upon xl, that's 1 upon j omega l. So guys, here I have written the magnitude straight away. Why don't we have that j over here? Why we have that j there? We have taken the magnitude directly. So plus 1 upon xc. Xc is what? Xc is 1 upon j omega c. So it flips up, isn't it? So j omega c, right? So guys, taking out this rt, this term is common from all the terms. So what do we have? What is taken out? 1 upon rt as common. If that is taken away, that's taken out, we have 1 plus 1 upon rt came out, so we have rt. And guys, this j over here, okay, which is positive j in the denominator, can be written as negative j. Okay, I've told you the reason just now. Negative j r total by omega l. All right, so even this one plus j omega c into rt. Why? Because rt is taken out as common, isn't it? Rt, close the bracket. So guys, right, so a small important manipulation over here, you have to watch carefully. Will that be any problem if I do this? Will this be any problem? Well, like, would that be any problem if I go for this one? Omega naught upon omega naught gets cancelled and the same result, isn't it? So on the other hand, we have, would that be any problem if we go for omega naught by omega naught over here? I suppose we don't have any problem. So guys, here it's y, we are in search of y. Okay, 1 upon rt, 1 upon rt, 1 plus j, this one, okay, plus j. I've written that down, that one. So can you see something? So guys, can you see something? Can you see a product? Can you see a hidden q over here? Can you see a hidden q? We have a q. See this product, omega multiplied with r into c, omega r c. Even this is a q, right? So here and so including that omega at resonance, all these came into picture considering the resonance condition, isn't it? So can you see omega multiplied with c multiplied with r, this is a q. Okay, so omega into c into rt. We have some suffix over here, so the author says, the expert says it's a q, but some suffix given, effective q, eff, effective q value. So if this is q, well, j has come out, this is q, and what is left over? What is left over here? It's this ratio is left over, omega by omega naught is left over, isn't it? And from here, even we have a hidden stupid q over here, a hidden q. Where is that? Let's find out where is that hidden q. So negative j, okay, negative j, and where is that? R by omega l. Okay, we have I erased that one. We have r by omega l, r upon, even this is a q value somewhere. I have erased it away. I have written it previously. Yeah, r, yeah, this one, r upon omega l. It may be r, may be in any other form, omega may be in any other form, and l, that ratio r upon omega into l, it's a q value. So q, that can be written as a q, right? So if we have taken this away, which ratio is left over? It's a, what is left over? Once again, omega naught by omega, omega naught by omega is left over here. Okay, so this one. So can you see this? Is that clear? So guys, yeah, y will be equal to 1 upon rt, which is common, and 1 plus J Q effective, and here J Q effective, J Q if it's even if it's that effective, okay. So because we have that same omega naught and something, some suffix over here, okay. So even that is Q effective, same Q, the resultant will be same Q. So J Q effective as common from these two. So what do we have? So what do we have here? The first term, omega by omega naught from here minus this one, okay, this one, and this is for here completely, and omega naught by omega naught by omega. So close the bracket, and this one we need to have, we have this one, isn't it? So we need to have this one. All right, so hope you understood the reduction over here, and something else over there, something else, a small assumption over here. A small assumption will reduce the equation to a great extent. What is that small assumption? It's that let us say omega minus omega naught by omega naught. Let this be some del, okay, some del to reduce that equation, some del for some simplification. And at resonance, I've told you in the beginning itself, at resonance omega will be equal to omega naught. So at resonance del will be equal to, if omega equal to omega naught at resonance, if this that exists in the resonance condition, and what happens to del? So if this is same, 1 minus 1, that's 0, isn't it? So del will be 0 at resonance, remember, okay. Even that has to be noted down. At resonance del will be equal to 0. Why? Because at resonance omega will be equal to omega naught. And so what simplification can be done over here? It's C, omega, which will be equal to omega by omega naught minus 1 for this one, okay. So that ratio omega by omega naught will be equal to 1 plus del. This is negative, going that side it will be positive. So the ratio omega by omega naught will be 1 plus del. So that has to be plugged over here, expression for that one. So y will be equal to 1 upon RT, okay, 1 plus J Q effective, and this one omega by omega naught, it's a 1 plus del minus omega naught by omega, the reciprocal of this one, so it will be 1 by 1 plus del for this one, and we have this, so this should be closed, right? So we got to solve this one, so simplifying this one, let me do on this side. It's a 1 plus del by 1 minus 1 by 1 plus del. So the LCM will be 1 plus del, cross multiplying this one, this has to get cross multiplied, isn't it? So 1 plus 2 del plus del square minus 1. So the simplification of this one. So here what happens, this negative 1 and the positive 1 gets cancelled. So taking out 1 plus del in the denominator, it's as it is. 2 del as common from here, so we have 1, take it out, plus 1 del has already come out, so it should be del by 2 over here, okay. So this simplification plugging in over here, so y will be equal to 1 upon RT into 1 plus J Q effective, right? So guys, writing more precisely, this one, 2 del, we have 2 del from here, from this simplification, okay, from this simplification into Q effective, okay, and we have this one, so 1 plus del by 2 upon 1 plus del, okay. So at a frequency, at resonance frequency, if we have del equal to 0, we will be having that frequencies around resonant frequency, del will be very small. At resonance frequency, if del is equal to 0, the frequencies, for the frequencies around the resonance frequency, del will be very much small value. 1 plus that small value, we don't have this anymore. We don't have this anymore. Okay. And if del is small, half of del will be even more smaller, so we don't have this anymore. So what is that? Y will be equal to 1 upon RT. Go back to that statement. Okay, so at resonance frequency, del equal to 0, it's very much proved. So that frequencies around the resonance, we'll have a lesser value of del, smaller value of del. If del is small, half of del will be even more small, so that can be neglected. Okay, so here 1 plus j 2 times of del q effective will be left over, neglecting this one. This is change. Okay, and so here what are we in search of? We are in search of that z, which is equal to 1 by y, which is equal to the reciprocal of this one. So what we have is RT upon 1 plus j 2 times del to q effective. This is the z over here. All right, so what will be V naught? V naught will be equal to Gm. What's VB dash E? VB dash E is this one. See, from the beginning I have written. So Gm, it's a suffix. Okay, Gm transconductance, Gm into VB dash E can be plugged in with this one, V in into RB dash E by RB dash E plus RBB dash from that expression for VB dash E, and Z will be the reciprocal of this one. Okay, Z, no sorry, reciprocal of this one, this is Z, so plugging in Z as it is, RT upon 1 plus J 2 times del into Q effective, right? So we are in search of that ratio. Which ratio? What is that ratio? We are in search of the valid ratio will be V naught by V in, this V in, V naught by this one, V naught by V in, V naught by V in. These are all getting multiplied, isn't it? So V naught by V in, what is that? AV, voltage gain, AV, right? And there is a condition at resonance, I repeat, at resonance the del will be equal to 0, in the sense AV at resonance, the equation has a transformation, this will be 0. Okay, del will be 0 at resonance, so we have Gm RT into this one, what is that, RB dash E by the total resistance RB dash E plus RBB dash. Okay, so this is what happens for voltage gain at resonance. This becomes 0 and we'll be left with only 1 over here. Okay, so in that case we'll have to have a ratio, what is that, AV upon AV at resonance, okay, so what do we have? This one, this entirely over that Gm, all these gets cancelled. Okay, all these RT gets cancelled, Gm gets cancelled in that one. So finally what will be left over is 1 upon 1 plus J 2 times of del Q epsilon, right? So this exists in general, and at resonance this will be 0, so the reduction will be this one. Okay, and the magnitude, magnitude AV by AV at resonance, magnitude will be 1 upon magnitude of A plus JB, the magnitude will be what? Under root A square plus B square, isn't it? So the same thing, we don't need this anymore. Okay, so what is that? Under root 1 plus 2 times of del Q effective whole square as expression for the voltage gain. Make a note of this one. Why? Because we have an extension for this equation, effect of cascading on bandwidth. The expert starts doing something from here. The proof for that one will be from here. And I hope you understood the analysis. Thanks for watching.